Assalamualaikum and good morning, everybody. My name is Muhammad Zakir bin Zamli, matrix number 102768. We are from Group 17, and our project is about the design, simulation, and scaling of a ranking cycle system from 15 megawatt to 35 megawatt. Throughout this presentation, we will explain the cycle configuration, simulation approach, thermodynamic analysis, and the modifications needed to increase the power output. So this slide is about our table of contents, which shows the overall structure of our presentation. We will begin with the introduction and methodology, which will be explained by me, Muhammad Zakir, and then my friends will explain the design and simulation of the 15 megawatt ranking cycle. After that, we will discuss the mass and energy balance, thermal efficiency, and the modifications needed to increase the system output to 35 megawatt. Finally, we will end with recommendations and conclusions. So this is the introduction section. This project focuses on the ranking cycle, which is widely used in thermal power plants to generate electricity. It is a reliable system for converting thermal energy into useful power. The ranking cycle uses steam as the working fluid, and its performance depends on operating parameters such as turbine inlet temperature, boiler pressure, condenser pressure, and steam mass flow rate. These factors are important because they affect the power output and efficiency of the cycle. In this project, we used Microsoft Excel to simulate a 15 megawatt ranking cycle and analyze its thermodynamic performance. After that, we proposed suitable modifications to scale up the systems from 15 megawatt to 35 megawatt. And this is the methodology section. This slide shows the basic configuration of the ranking cycle and the assumptions used in our analysis. The cycle consists of four main components: the feed water pump, the boiler, turbine, and condenser. The pump increases the pressure of the water. The boiler converts it into steam. The turbine extracts energy from the steam, and the condenser converts the exhaust steam back into liquid so the cycle can continue. In this simulation, we used ideal ranking cycle assumptions. The system is considered to operate at steady state, while the pump and turbine are assumed to be isentropic. We also neglect heat losses, pressure losses, and changes in kinetic and potential energy to simplify the thermodynamic analysis. So this slide explains the simulation steps carried out in Excel. We started by entering the main operating conditions for the ranking cycle, including the pressure, temperature, and mass flow rate. Then we determined the thermodynamic properties at each state point. After that, Excel was used to calculate the work produced by the turbine, the work required by the pump, the heat supplied in the boiler, and the heat rejected in the condenser. From these calculations, we obtained the net power output and thermal efficiency. The final step was to check whether the cycle achieved the target output of 15 megawatt. If not, the conditions were adjusted until the required power output was reached.
Hello, my name is Janice Lim Anchi, metric number 110282, and I'll be presenting about the design and simulation of 15 megawatt ranking cycle and mass and energy balance analysis. For the phase 1 in the simulation, the targeted net power output was set at 15 megawatt. The simulation was based on a simple ranking cycle that consists of boiler, turbine, condenser, and feed water pump. The selected operating condition were a turbine inlet pressure of 8,000 kPa, turbine inlet temperature of 500 Celsius, and condenser pressure of 10 kPa. Based on the steam table data, the turbine inlet enthalpy was taken as 3,400 kJ per kg, while the turbine inlet entropy was 6.727 kJ per kg K. The turbine expansion was assumed to be isentropic. This means that the entropy at the turbine outlet is equal to the entropy at the turbine inlet. By using assumption, the turbine outlet's condition was determined at the condenser pressure. From the simulation, the turbine outlet steam quality was calculated as 0.8104. and the turbine outlet enthalpy was 2130.43 kg per kg. The steam quality value of 0.8104 means that the steam leaving the turbine contains 81.04% vapor and 18.96% liquid moisture. This indicates that the steam becomes a wet mixture after expansion. This is important because high moisture content at the turbine outlet can cause erosion of turbine blades and reduce the efficiency of the turbine. Overall, in Phase 1 simulation, it shows that the selected operating conditions are suitable for achieving the required 15 MW net power output. The obtained values for turbine outlet quality, enthalpy, and mass flow rate were then used as the basis of the mass and energy balance analysis. For the mass and energy balance analysis part, the mass and energy balance analysis was carried out for major components of Rankine cycle. The main energy interaction considered were turbine work output, pump work input, boiler heat input, condenser heat rejection, and net specific work output. The turbine work output was calculated using the enthalpy difference between the turbine inlet and turbine outlet. Based on the simulation, the specific turbine work output was 1269.57 kJ per kg. This confirms that turbine is the main component responsible for producing useful work in the cycle. The pump work input was then calculated using the pressure difference between the condenser outlet and the boiler inlet. The pump work was found to be 8.08 kJ per kg. This value is so much smaller than the work output because the pump handles liquid water which require less energy to compress compared to the steam expansion in the turbine. The net specific work output was then calculated by subtracting the pump work from the turbine work. The net specific work output of the cycle was 1261.50 kg per kg. This value is important because it was used to determine the steam mass flow rate required to generate the target power output. The boiler heat input was calculated from the enthalpy increase between the pump outlet and turbine inlet. The condenser heat rejection was then calculated from the enthalpy decrease between the turbine outlet and the condenser outlet. This value shows that the largest energy interaction in the cycle occurs during heat addition in the boiler and heat rejection in the condenser.
Hello, my name is Angel Anikalista, anak Sonny William, metric number 107831, and I'll be presenting the thermal efficiency analysis and modification of 15 MW to 35 MW power generation. For the thermal efficiency analysis, the steam mass flow rate required to generate 15 MW of net power output was calculated using the net specific work, which is 1261.50 kilojoule per kilogram. After the calculation, which can be seen in the slide, it is calculated that the steam mass flow rate required is 11.89 kilogram per second. Therefore, 11.89 kilogram per second of steam is required to continuously flow through the turbine to produce the desired 15 MW net power output. The thermal efficiency calculated, which is 39.42%, means that less than half of the heat supplied in the boiler is converted into useful network output. The other 60.58% is heat being rejected in the condenser. Next, the modification of 15 MW to 35 MW power generation. There are two proposed modifications, and the first one is by increasing the steam mass flow rate through Rankine cycle while maintaining the same operating conditions. The net power output of a Rankine cycle is directly proportional to the steam mass flow rate, where an increase in steam mass flow rate will allow for more energy to be converted into mechanical work by turbine. From scaling and modification in Phase 2, increasing the mass flow rate to 27.74 kg per second will allow us to reach a 35 MW net power output. The second modification is implementation of reheat Rankine cycle. In a reheat cycle, boiler pressure and temperature are elevated and the steam expands partially through a high pressure turbine before returning to the boiler for reheating. Their heated steam is then expanded through second turbine stage to generate additional work. So from phase 2 of scaling and modification, increasing the pressure and temperature of boiler will increase the amount of heat added into the system with the steam flow rate of 24.14 kg per second. This can help us reach the net power output of 35 megawatt, while the thermal efficiency will also increase to 42%. To compare these two modifications, the first modifications offer a straightforward approach to increasing power generation because it only requires an increase in steam mass flow rate. For the second modification, it improves both power output and thermal efficiency through thermodynamics optimization of expansion process via turbine.
Hi, my name is Muhammad Elhani bin Adun with number matric 108208. I will present recommendation and conclusion part. For recommendations, several recommendations are proposed to improve the accuracy, efficiency, and reliability of the Rankine system cycle. First, actual turbine and pump efficiencies should be incorporated instead of assuming ideal isotopic process. In real industry power plant turbines and pump experience losses, so using actual component efficiencies will make the simulation more realistic. Second, economic and environmental evaluation should be carried out. Economic assessment is important to determine the feasibility of the proposed power plant design, while environmental assessment is needed to evaluate the environmental impact of the system. Third, advanced simulation software such as Aspen HYSYS or Aspen Plus can be used in future work. The software tools can provide more accurate poverty estimation, detailed process modeling, and better performance evaluation compared to Microsoft Excel. In conclusion, 50 megawatt Rankine cycle power generation and the scale up to 35 megawatt system was successfully designed and stimulated using Microsoft Excel. An appropriate design of 50 megawatt Rankine system provide an excellent reference point. There is two modification were proposed to scale up the network power output from 50 megawatt to 35 megawatt. First, increasing in system mass flow rate allow for 50 megawatt net power output under same operations condition. Second, reheat and regeneration increase the thermal efficiency of the cycle. The simulation provide insight for further analysis of the cycle. Overall, Rankine cycle as efficiency and reliability technology for modern generation. Thank you. That's all from Group 17. Thank you.